Hey, I'm going to talk about max cut. So what's the problem? Max cut. So we want to find a bipartition so that we could maximize the total number of edges going from one set to the complement set. And the set S is a subset of all your vertices of the graph. And as you know, this problem is NP hard, and that's the reason we want to approximate it. So this is another approximation algorithm. So the max cut is M if and if G is bipartite. So this is the biggest cut. If it is bipartite, so the max cut is M. And so we want to see how close the graph is to being bipartite. So a classical thing is that a random cut, let me define to be a random cut, which is when we put a vertex with probability half, and a random cut, I want to prove it that it is a half approximation. The proof is very easy. So the theorem is that the expectation of the number of edges going from S to S bar is greater than M half. And so the proof is very simple, because for each edge, if, for example, x of that edge is 1, it means that E is cut. Otherwise, it is not. So the expectation of that random variable is the probability of xe equal to 1, because the value is 1, so the probability is equal to expectation. And this is equal to half. So the expectation of the number of edges going from S to S bar is the expectation over the sum of all these, any edge. So if it is 1, then it is cut. Otherwise, it is not. And so it is by linearity of expectation, you know that this becomes expectation of xe, and because, for example, 1 over 2 plus 1 over 2, and we have m edges, so this becomes n over 2, and this is the end of the proof. So we observe that since max cut is less than equal to M, then the random cut gives a half approximation. So the problem is, can we do better than half approximation? And the answer is that yes, we can use SDP, semi-definite relaxation, using random rounding, which instead of 0.5, which is the random cut, it gives us 0.8785 approximation, and this is a classical result. So the LP relaxation of max cut, so the integrality gap for the random cut is just half. We want to make it better. So let's formulate it using integer quadratic program. So in max cut, you can represent it as solving this optimization problem, which is integer quadratic program. Quadratic because we are using square, and I use 4 here because for simplicity. You will see why it is why you should use 4. And so x of any vertex is either -1 or 1. So x of v could be 1, x of v could be -1. So you always imagine S and S bar So some of them are 1, and then it is a cut. Some of these edges goes from S to S bar. So we assign to each vertex V, we assign xv. So it's just a scalar. It's not a vector. It's just a scalar. That's why it's so easy. And then we relax it because we want to really solve it. So relax it. It now becomes the interval between -1 and 1, and this is a continuous interval. So we relaxed it. And this optimization problem is just, if you I've written it in a different form in some of my previous videos, and you notice that it is so similar to the eigenvalues of Laplacian. I mean, the Laplacian, it is the diagonal matrix minus the weight matrix, and so you see, we are just dealing with this in another form. We just don't talk about matrices. We are working on that in a totally different framework. So now xv is a vector instead of just a scalar, and this is the idea of Goemans-Williamson. It is famous because they introduced this relaxation. It's a random relaxation. So we want to maximize. So the point about this is that, first of all, our labeling is not just to a scalar, it's a vector. So for any vertex v or u, the difference between the labeling of them, first of all, each of them is a vector. So xu is a vector, this vector. And so it is like before, it is a squared over 4, but this time xu and xv are vertices, are vectors. So we solve this optimization problem subject to that it is unit vector. And you know that it is a simple exercise to show that we can write this as the sum over, so this comes here, and of course this is, you can write it as xu minus xv, the dot product between this vector and itself. So if you just simplify this, then you do it like this. So it becomes xu squared plus xv squared minus 2xu, the dot product of xu and xv. And then finally all of them over 4. So if you solve it, because it is subject here, it is subject such that xv is 1, so this is 1, this is 1, and this is simplified to 2 minus 2 dot product of xu and xv over 4, and this is m over 2 minus 1 over 2, the dot product of xu and xv over all edges u and v. And so now the problem is just, because we want to maximize this guy, so it is equivalent to saying that we are minimizing this guy. So we want to minimize, so the problem formulation has been converted to another problem, which is minimization of this, the sum of all dot products for any vertex. And same as before, x of v, it is a unit vector. And this is the SDP problem. This is SDP, semi-definite programming, which is a generalization of linear programming. And so let's carry on and see that let's define a variable for convenience. Let's define variable y, which is that dot product between two vectors. And so the goal is just to minimize y uv. So it's just a simplification of our formulation for any v, y vv is 1. So we write the SDP like this, and we use the ellipsoid method to solve the SDP in polynomial time. If you write the Y matrix, which is X transpose X, this is the Gramian or Gram matrix. I'm sure you have heard it in machine learning several times in several problems. So it's just the dot product of all of the combinations. XV1, XV2, up to XU1, XV1, XVN. And here XV2, XV1, XV2, 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 XVN. And then XVN, XV1, XVN, XVN. For example, here is just Y, Vn, and Vn. And so because we have unit vector constraint here, so it is 1. And this is the Y is the matrix of dot products. So let us define M. What is PST, positive semi-definite matrix? M is PST. You have seen it in machine learning several times. So M is PST if M is symmetric and we have something and here. And for any Z, Z transpose MZ is greater than 0. And the claim is Gramian matrices are positive semi-definite. And the proof is very simple. We just write Z transpose YZ and see what happens. Instead of Y, by definition, you can write X transpose X. So you can rewrite it as this one. And this is greater than 0. So we have proved this claim. So SDP is a linear program over entries of that positive semi-definite matrix. So the strategy is that you have max cut relaxation. First you should solve this SDP problem. YVV is 1 and Y is positive semi-definite. They write it in machine learning or any context like this. This is greater than 0. And after solving this, you give this problem to an SDP solver, and SDP solver gives you Y. But what we want is X. So we give it to Cholesky decomposition to get X. So if you want to search it, this is Cholesky factorization. You can learn about it after this lecture. So Y is X transpose X, and M is positive semi-definite if all eigenvalues of M are non-negative. And Cholesky decomposition, it is doable because this guy, you can use just SVD of y, so it becomes V transpose V, and you know this is the diagonal of all eigenvalues, and this is the all of them are eigenvectors V1, V2, and if you solve this, then it becomes, if you write this and simplify this, you can write it like this. Because this one is diagonal, so you can write it like this. Times V, and this is just V transpose sigma V, and this is X transpose, and so we have written it like this. So Cholesky factorization is doable. And then any matrix Y, which is a vector in Rn2. I mean, this is a matrix, okay, n by n matrix. But if you vectorize it, you can have this vector. So for us, it is just another linear program over the entries of this matrix. That's why we always say that semi-definite programming is just a generalization of linear programming. So if you have some domain, and then you have some restrictions, then the boundary is sometimes like this, it is curved, and sometimes like linear programming like this, and sometimes it is like this, and sometimes it is straight. So it becomes this area, and this area is convex. This is convex, and the region of positive semi-definite matrices is convex. And the proof is very simple, because we take two positive definite matrices M1 and M2, and for any Z, we just need to show that just the linear combination of them, for example, mu M1 plus 1 minus mu M2 is also positive. And if we prove this, then this area of PSD matrices is convex. And if you simplify this, it becomes mu Z transpose MZ plus 1 minus mu Z transpose M2Z, and this is greater than 0, because this is positive definite, this is positive definite, and our proof is complete. So to run the ellipsoid, we need a separation oracle, as you know. And the separation oracle is that for given any y, determine if y is in C, or output a separating hyperplane. So if y violates any linear constraints, we have a separating hyperplane. So for example, here, this is Z transpose, and this is PSD area domain, which has lots of matrices. And here is y. So if y is not positive semi-definite, then, so if not PSD, then there exists a Z such that Y transpose, Z transpose YZ is less than 0. And Z transpose YZ is equal to ZI, ZJ, YIJ, and it is Z, you can write it as ZZ transpose dot Y, and in other words, we have found that there exists a Z such that we can find such a Z such that this guy is less than 0, and this is the separating hyperplane. And so separation oracle for SDP is, I just review it, is first you check if Y is symmetric and satisfies the linear constraint. If not, defines that separating hyperplane. Second, we compute the smallest eigenvalue of Y in corresponding Z. So if eigenvalue is greater than 0, Y is PSD. Y is PSD. And we can certify that Y is feasible. If not, Z transpose Y